Hello everyone and welcome back to another MECH 220 video. Today we'll be covering angular momentum in 3D. This is chapter 21. Specifically, we'll be covering example 21-36 from section 21.2. So let's go ahead and read the problem. The 15 kilogram rectangular plate is free to rotate about the y-axis because the bearing supports at A and B. When the plate is balanced in the vertical plane, a 3-gram bullet is fired into it, perpendicular to its surface, with a velocity of negative 2,000 I hat meters per second. Compute the angular velocity of the plate at the instant it is rotated 180 degrees. If the bullet strikes the corner D with the same velocity V instead of at C, does the angular velocity remain the same? Why or why not? So, as always, I wrote down some notes here that are relevant to this problem. The first one being about planes of symmetry. So the rule is you need at least two planes of symmetry for products of inertia to be zero. This is important to take into consideration because when you're dealing with 3D, you're not only dealing with 3 moments of inertia, you're also dealing with 3 products of inertia. And because you're working in vector form, you would have to compute 6 different things. So doing this is not only correct, but also it simplifies your problem by a lot. So continuing on this, if we have a single plane of symmetry, then the only non-zero product of inertia will be that plane. So some random example here that I've written that has nothing to do with the problem that we're doing, but just to give you an example, if plane xy is symmetrical, but xz and yz are not, then the product of inertia of xy is not zero, but the product of inertias of xz and yz are zero. Then I have here the sign rule for the cross products. Note here that says define a system, and this is important when you're dealing with conservation of momentum or conservation of energy, because depending on your system, you might not have conservation of momentum or energy. So it's important. And then here, the condition for conservation of momentum. If you see here, the principle of angular momentum, which is angular momentum at 1 plus the integral from time 1 to time 2 of the sum of moments dt is equal to the angular momentum at 2. In order for conservation of momentum to hold, the external moments must be 0. So reasonably, if you just, that goes to 0, then h1 is equal to h2. So let's go ahead and start the problem. So step 1, we define our system. Here I will define the system to be the bullet plus the plate. What does this mean for us? The motion that the projectile causes the plate to have is all internal to the system, so there are no external moments. Therefore, the angular momentum with respect to AB of 1 is equal to the angular momentum with respect to AB at 2. So the next thing that we're going to do is we're going to unpack all of this. Now this notation is very important. Well, for starters, this will be 0 because the plate is not moving to begin with. So I'm just going to take a moment to expand on the right-hand side for a second. So the right-hand side of the angular momentum is the vector HAB, which is essentially all the moments and products of inertia multiplied with all of the angular velocities. And this is in z-axis, x-axis, and y-axis. So normally you'd have a very long expression with the moments and products of inertia in the I hat, j hat, and k hat direction. However, in the case where the axes are the principal axes, so we're just dealing with x, z, and y, and of course all of our products of inertia are 0, this term here, which would originally be very long, essentially just reduces to this. So we just have to deal with these 3 terms. So let's unpack the motion of the bullet first. So initially, the bullet only has translational angular momentum, and that is expressed by this here. R, we know it to be 1.5 k hat, since that's the total distance between the bullet's height at C and the shaft AB cross the mass, which we know is 0.03 kilograms, which is the mass of the bullet. And then as for the velocity, they have given it to us here. Now, if you notice, our left-hand side is only a component in j hat, which means when we take our right-hand side, we can say immediately that the angular velocity at x will be equal to the angular velocity at z, and that will be 0. And if you still don't believe me, I'm going to write it out like this. If you look at this, there are no components in I hat or k hat on the left-hand side. So essentially, that's this equation is the same thing as saying this. And since the moments of inertia of AB at x and z aren't 0, therefore the angular velocities at x and z must be 0. So this simplifies our problem a great deal, because the only moment of inertia we have to find is at y. So in order to find the moment of inertia about AB, we'll have to use a method, or rather an equation called the parallel axis theorem, which is the moment of inertia at the center of mass plus the mass times the distance to that center of mass. Now, if we look up here, I've already pasted the moment of inertia about the center of mass for a thin plate, and essentially we'll be using this one for that. And as for the distance between G, which is here, and the height G here, this is 0.075, which is half of 0.15 meters. So the distance between G and the bar AB is 0.075 in the k direction. So there's no motion in x, it's just z. So this will be 0.125 kilograms meter squared. And finally, we can use these values to solve for the angular velocity of the plate at the impact. Now, this is only the first part of our problem done. The second part of our problem aims to actually answer the question. So we needed the initial angular velocity of the plate in order to use conservation of energy to find the angular velocity of the plate after an angular displacement of 180 degrees. So this is essentially why we used angular momentum to find the angular velocity of the plate just after the impact with the bullet. So now we're going to work to solving the problem. Now, because of the system that I made that included the bullet and the plate, there are no external forces to the system, so we can say that the energy is conserved. Right, so what I'd like to do is to write out all the terms separately, and then plug all the values in at the end. Initially, we have our height. That's going to be at 0.075 meters, which is the distance between the bar AB and G. At 180 degrees, this whole plate will have flipped, and will in fact be down here. So this point G will be at equal distance G prime. So this G prime will be at equal distance to AB as G was to AB, except it will be in the negative direction. So that's how we're going to interpret the change in potential energy. For T1, now the full expression of T1 would be the translational kinetic energy plus the rotational kinetic energy. However, since our rotation is happening from the bottom of the plate, this will essentially be 0. And what do I mean by that? I mean, it's the difference between a rotating bar that is rotating about point O and a bar that is rotating about point G. A bar that is rotating about point O will only have kinetic energy that is rotational, whereas a bar that is rotating about G will have kinetic energy that is rotational and kinetic energy that is translational. So in this case, because the plate, we're looking at the plate from AB, that's essentially, it's this case right here. So we will have no translational kinetic energy in this case. So T1. Oh, and we can sort of dispense with the vector notation since we're only working in J. We don't have to distinguish between the different coordinates. So really it's just 1/2 -8 squared, because if you unpack this here, it is AB times AB. So if you multiply those two together, you get omega AB squared. And that is times our moment of inertia, which we calculated to be 0.1125. And finally, T2. And this is what we're searching for. And if you compute all of that, you should get 21.36 rads per second. And that is your final answer for the angular velocity of the plate after a rotation of 180 degrees. So now it's time to address the little extra part to this problem, which is if the bullet strikes the corner D with the same velocity v instead of at C, does the angular velocity remain the same? Why or why not? So the angular velocity does remain the same because the height between D and C is the same. Nowhere in our computation did we ever take into consideration this distance or any horizontal distance. It was always the distance between G and the bar AB, this vertical distance. So if you take the point D, which is at the same height as C, then these vertical distances are all the same. And if you go ahead and plug all those vertical distances into all our steps and all our equations, you would get the same answer. All right, that's the end of this problem. Thank you for listening.